Okay, so here is one last video for class 10 of ME370 where we're talking about FEA. This is just for displacement or for deformation, right? Deflection, any of those D words. So here's an example. I did this in class 9. We got results of 0.287 in the y direction because of this force and 0.0831. I actually did this in the showed the results of this in the video for class 9. But let's do it again. Let's actually do like sort of a tutorial for the thing. Speaking of tutorials, I should mention that there's resources under the useful links and resources on our Blackboard page. Down here I have FEA resources. I have a variety of things here that you might find useful, including, oh look at this, a theoretical manual for Solidworks Simulation. I don't even know what that is. Maybe I should have used that in class. There we go, theoretical manual from 2014. But anyway, looks to be a long document. Let's see, how many pages is this? It's pretty long, yeah. But anyway, it's like 115 pages long. There it goes, I can see at the bottom. But I could tell you a whole bunch of things about what's going on underneath the hood. So maybe this would actually be really good. And it might actually have some amount of tutorialness to it. So you might want to check that out. This looks like it's going to be a pretty good research. You know, they're talking about some of the matrices operations. It might actually give a little bit more detail about the coordinate transformation and that kind of thing, and principal stresses. All right, good. So this will be relevant things that you might want to look through if you want to dig in deeper into what's happening underneath the hood. But I also have what I thought was a pretty good one is a CRC book, and I think this is a pretty long book as well that I found from somewhere. Yeah, it's 348 pages, Introduction to Using Static Analysis Using Solidworks Simulation. So I bet this has some pretty good content in it. I need to look through it a little bit further and see what kind of stuff we might want to use in class. Right, and but it would give you more detail than what I was presented in these videos, and I think it's I think you'll be interested in. So let's take a look at doing this problem right here, where we have a part, and we'll create a new part, and it's basically the same part. So I almost kind of wish we were working on something else, but it's and now we're just going to match up the displacements that we had. So once again, I'll try to align everything. Well, it didn't really actually give us an X, Y, and Z. By the way, I should mention this is a problem in Chapter 4, but they actually want you to use Castigliano to get the answers. And I showed that in the previous video, or not the previous video, the video for class number 9. So check that out when you get a chance, and you could see that from the solution manual, I got pretty darn close to the answer. All right, so then this one is in inches, and they show that it's 15 inches long in that direction and 7 inches long in this direction. And so that I could just use the sweep function, I need to make a fillet. And half an inch, let's see, what's the diameter? This is a half of an inch, so we might actually want to go up to a little bit more. And as I mentioned, that might be something to look in a little more closely and see if that has an effect on the results, or what kind of effect it does have on the results. And doing those little side study kind of things, that is, in essence, in my opinion, FEA, right? It's more than just making a model and solving it and finding the answer. It's making a bunch of models and changing the model and seeing the cause and effect of various aspects, so you can get a better overall understanding, insight. That's the word I was looking for. You want insight into what's taking place. So I wasn't doing a very good job of a tutorial because I didn't just tell you what I just done. So let me get rid of this right there. Okay, so what I did is I made this on the top plane. That was my strategy, And then so I'm looking at downwards in it. Now I'm going to go onto the plane that's over to the side right here on that right plane and make a sketch on there. So I didn't announce that I was doing that. And I'll make a circle using the origin. It's just convenient to do that. And I will make this 0.5, which is the diameter of the piece. And I'll accept, and it was highlighting those sketches, but I decided to click somewhere on here and unhighlight it. And now I'm going to go to Features, and I'll go to the Swept Boss Base. And you can see that they have a little circle here. So we want to either pick that sketch, or I like to use this tree right here. We can pick the sketch, pick the entire sketch from that. And then you go down to this one, you see that's highlighted pink. And we can pick that sketch, and then it gives us a preview. So we can see what this thing looks like. So that was simple enough, I guess. And then now we go to simulation, and if you hadn't seen in the previous video, you got to make sure that if you don't see it up there, go to add-ins, go up to this little gear, go to add-ins, and you can click the Solidworks Simulation right there, or click this button and it'll come on every time. So you go to simulation right here, or up to here, and just go to study, or you go to here and go to new study, and we have static as our only option. I think there should be other things turned on right now. I gotta ask somebody about that. Learn more how to get the complete package. But for right now, that's going to be good enough for us. And we go down this list. Now, this actually kind of fits into sort of like the basic descriptions of the process of doing an FEA model. We did the modeling part. And then we apply materials is our next thing. So we're going to right-click on that part that we made and apply the material. And this is, again, this is steel. And I think in the original problem, I guess I gotta have to look back and see what I used as part of that. Let's see. Do I have that written out somewhere? I must have that written out. I said to use I don't know if I ever said what to use. It says steel. So what I use? I use 30 million. Yep, I use 30 E6. So let's change this to English units, and you can see the elastic modulus is 30 something and change. That's 20 something and change. If I go to alloy steel, this is 29 million. I don't know if we got to try to hunt and pack here for the 30 million. Yeah, plain carbon is 30.4 million. That might be the way to go, to try to see if we can get as close as possible. If I used 30 million in the hand calculations, here you go, this is close. Even though it's like 201 annealed stainless steel, it doesn't really matter. Although the Poisson's ratio is only 0.27, but I don't think it's going to actually matter. I think it's really the elastic modulus is going to matter. That's pretty close. Is there anything better? Let's see. Now it's 29 million, 29 million. Okay, we're going to stick with this guy. Just see how close we can get. So I hit apply. The window doesn't go away, it just stays there, so I had to hit close. Connections, as I mentioned before, that's only useful when you have multiple parts, when you're doing an assembly that you pulled in, and we only have a part. We have fixtures. I right click. Once again, we're going to make a fixed geometry, but there are other boundary conditions that we can put on. These fixtures are boundary conditions. So I'm going to fix geometry, and I'm going to click on this face right here. And now I want to put loads on, so I go down to the next one in this tree. And this is something that you do in any FEA code. It's pretty easy to do in SolidWorks. I'm going to put the load right here on this face, but I want to select direction. I want to use English units, and in this direction, right there, it's not giving me a preview. And when I select direction, by the way, I need to pick something as the basis for the direction. I'm going to pick the same face right there. So now when I go to there, yep. So that was the direction that we were going. And in here, I think because it was a 3, 4, 5 in the this direction right here, it'll be 9, downwards 12, in the x direction 9. So this goes 9 pounds. And in that direction, whoop, it's going up when I want it to go down. We go 12 pounds. We're good, we're good. And we're okay. Now let's hit the mesh, and we're just gonna pick a, let's actually make a crude mesh. Let's make as coarse a mesh as I can on this one and see what happens. All right, it wouldn't let me even make a rougher mesh than this. We kind of like look and see. That looks really weird. See, there's a little skew going on there. That's definitely some weird looking elements. It's not looking pretty, but we'll see what happens anyway. We'll hit run. So we go up to the top. All right, so I meshed it, discretized it, and I hit run. All right, so that's solved pretty quickly. I'm going to go to displacement, so I'm going to right click that and hit show. It's showing me a color plot right here. I need to control what it is that I'm seeing here. So I go to edit definition. I'm going to separate them between, so it's giving me the total, the ultimate, like, so it's just going to be the square root of the sum of the squares of the x, y, and z deformations that could be taking place here. I want to go to y first. Let's just take a look at y. And I want it to be in inches. So I need to pull that next one down. I'm going to leave the deformed shape at the default, but you notice that it's, if you can read that, it's 5.43 times what the actual deformation would be. We could actually superimpose what the, it's supposed to superimpose. It's not like actually showing here, but it's usually superimposes, I think that's the word, what this thing will look like onto, I think it was. Let's see if we can see that. I don't know if it just makes a difference to how transparent the original, the undeformed sheet is going to be. And under here, let's see, this is, oh yeah, this is a scale. We could change what the scale is. Sometimes what will help us is we might want to put the number of significant figures. It's going to go scientific notation. Let's just leave it that way. All right. So let's go to, well, okay, so one way that we could have done this, let me go back to chart options, is we could go to show minimum right there. So they show us this minimum so we could find out what the value is. Another way that we can find it is we could also go to plot tools, pull this down. One, we could go probe, right? And a probe is just going to give us, we could touch at various spots, it's going to give us a node average, a node at wherever we pick right there, right? And it'll give us a value. Sometimes that could be good. I like to use this one called list selected. All right, so now you're going to pick a surface, like I'm going to pick this surface right here, and I'm going to hit this update, and it's going to give me the values in this list right here for all of them. And then down here at the bottom, it's going to give me the sum of them, which I don't know why you'd ever need. It's going to give me the average. It's going to give me the max. And it looks like the max and the average are the same. So sometimes I like to use the average, like right there at that spot, as opposed to, but there's really no difference right there. Let's get the, you see that there is the minimum is a little bit different. So actually the minimum would be 2.809. That's funny, but the average is 2.773. So that might be the one that I want to compare, right? Now remember, we made a bend right in there. So that might affect the results, but our mesh might affect the results. So right now, we're doing pretty well. We have 2.287 compared to 0.277 as the average, 0.274 is the maximum, 0.2809, that's like really close because we have 0.287, so we have effectively 0.281, so that's mighty close. But let's see if we could do better by way of doing a better mesh. Let's create a mesh, and because it's not that hard to do, let's just make it a really fine mesh. So you can see it made many more elements to it. And so like if we look through here, you can see through the cross section of the thing, there's a lot of elements. And that might improve it. Maybe. We'll see. We'll run it. And Is it going to give me that convergence plot? Nope, it still went too fast. Okay, so I'm going to go to my displacement again, hit that show, and you can see that we have a minimum of 2.831. It's really not that much different from what we had before in the previous mesh. We hit that update, and we see we have let's see, the average 0.27, yeah, 0.28 really, 0.2795 is the average that's taking place there. So that's pretty close to our 0.287. But when I went, okay, there you can see the undeformed shape right there, so you can kind of see what that looks like. It's kind of nice to get an idea of what that what the overall deformation is going to be. All right. Remember, from this one we had a lot of different things going on. That was also moving in the x direction as well as the y direction. Let's see. Let's go back to the modeling thing here, and I can just go ahead and this view right here, I guess I'll edit it. Let's, whoop, no, that's the wrong one. We wanted this one right here, right? Yeah. Let's see if it'll let us make this into 0.5. Right, so much smaller. Yeah. Actually, we could even go smaller. Let's go smaller. Let's go 0.25. See, will that make it too small? No, that's okay. See, I was worried about that happening. It's going to go to 1 point. It might actually have a hard time meshing that. Sometimes that kind of thing, if something converges to like a single point, it wants to try to figure out to make an element. Because this line exists on the model, it'll try to make nodes along that line. And that's actually something we could trick it to do by adding something called split lines that we'll learn about later. We could add split lines onto something so that we could force a node to go into place. But let's see if it'll mesh. This might cause it to, oops, don't want that. I'm going to hit just mesh. So I'm just going to create a mesh. Sometimes it'll give it a warning that you're getting rid of too many things. Okay, you see, it failed because of that point. All right, so these are things that you have to learn along the way, that there's certain things that are going to make it so that it doesn't work, and it can be very frustrating. But I'm going to change this back up to 0.5, and I believe it will mesh now because it doesn't have to worry about that one little point right there. But if you didn't know that from experience, you might get frustrated by this, but it should mesh now. Yeah, see it meshed. And you can see that, like, right along there, there's a node right along that curve, and there's a node right along that curve. It's the thing is that they couldn't figure out a way how to make how to mesh, because we had that one like little hard point that it went down to. We got mad. So let's see if this has any amount of influence, and it's going to running. It's running. Boom. How come it went the wrong direction this time? I don't know. Did I flip this thing? You know, it might have been, I don't know. That's a little quirky thing there, huh? Let me fix this. I'm going to edit that and reverse the direction. Not that one. This one? I think so. I think that's the one I want, right? Okay, it should be 9 going that way. Huh. That's weird. This reversed the things. You gotta be careful. That's a little weird. Like, let's see. Let's turn this one off. And this one is the one that's supposed to be 9. That's odd. I gotta be on the lookout for that kind of thing. All right, there's both going in the right direction. I think so. That should be the downward. Should be 12. Yeah, that should be 9. Interesting. Probably because I changed the model. Let's see, the mesh is fine, it's just I gotta rerun it. There you go. Any small models used to mean like it could be like an hour long for, like, I guess, you know, we're talking 20, 30 years ago, but we're going to show the displacement, and I think that got better. I can't seem to recall. Let's take a look at the average one and see how much closer it got to, I think it got a little better. The average 0.281, 0.287. We're good. I think we're good. Let's go in the X direction. Now, actually, what we could do is we could copy this one. That's what I do sometimes. I'll copy it, and then go to this and hit paste right there. All right. So we have this. We'll show that one, and now we'll edit the definition and make this in the X direction. Then we don't. Then if we want to go back and forth to it, we don't have to redefine it all the time. So this is the X direction. We don't want the minimum in there. We actually want the maximum in this time. The minimum doesn't tell us anything really. Go to the maximum deformation right there. All right, so boom. You could see, and we got 0.0855, right, as compared to 0.0831. All right, so that's actually pretty good. Right, and you can see that it kind of like moves outwards, right? It's being bent outwards because of this moment that's causing a deformation, and it's actually going to move in the Z direction too. Even though there's not a force in the Z direction, this thing is bent. It's going to have a moment that's going about the Y axis that's going to cause it to move in the Z direction. If we want to get the average of this, which is what we were doing before, so I might as well be consistent and go into that face and hit here, and we get an average motion of 0.0819. Right, so yeah, these are good results to make a comparison. But you can, this is a good experience to be able to calculate something by hand and get it to match in FEA. One last thought when we're talking about convergence and that idea. In this example of the concept of convergence, I talked about stress, and stress is harder to converge than deflection. FEA is very good, much better in doing a deflection analysis than it is at doing stress, actually, and usually converge much sooner to a known solution when it comes to deflection. So that's all I have for this little video that went longer than I expected. But anyway, I hope it was useful to someone.